We draw force acceleration diagrams to help us to see the way in which several forces acting on a particle can influence its motion. Do the forces balance? Does it stay where it is, or does it start moving in a particular direction? And a force acceleration diagram helps us to see what's going on. Now, we always draw the particle that we're interested in as just a box. So we're basically, it could be a car, could be a person, could be a conker, could be an aeroplane, could be anything. Just draw it as a box. And then all the forces acting on that particle come out of the box. That's really, really important. I'm going to put a circle around it. Out. They come out of the particle and they're represented with arrows. So you might have an arrow representing the weight, an arrow representing something pulling something forward, that kind of thing. And depending on how complicated your situation is, you might end up with various arrows coming out like that. So that's what a force acceleration diagram looks like. Now, if you're clever, you'll be thinking, I can see why that's called a force diagram, but why is it called a force acceleration diagram? And the reason is that we also add to our force acceleration diagram the information about whether or not the particle is accelerating, and if so, which way. And this is shown with a double-headed arrow, and it is not coming out the particle because it isn't a force. Acceleration isn't a force. It's just to give us some more information about what the overall effect, the net effect of all of these forces is on this particle. So that there is an example of a force acceleration diagram, and that's what you're going to learn to draw. So what forces might you be putting on your particle? Well, almost certainly weight. Weight is mass times gravity, and it acts towards the centre of the Earth. So just straight down, because it's the Earth that's causing that force. The normal force is a normal reaction, put the word reaction on, and this occurs when we have contact between the particle and something else, like the floor or a hill or something like that. So whenever you've got any contact between your particle and something else, you get a normal reaction. Usually we use R for the normal reaction, and that is really important that this goes perpendicular, so that's at right angles to, perpendicular to the plane, so that's the sort of surface of contact. So the floor, the hill, whatever it's on, you have to go, so if this is the thing your particle is on, then your normal reaction goes off like this, and that is at right angles to the surface that the particle is sitting on. Okay, tension. Not surprisingly, we use a T for tension. So tension might be in a string or in a tow bar, if that's what's pulling the particle along or pushing the particle along. Friction, which we use fr, and there's a separate video on the difference between static and kinetic friction, and so you can use just fr for now. And friction always opposes motion. That's the direction it goes in. So if the particle is moving, the friction will be opposing the motion. If the particle is not moving, it will be opposing the attempt at motion. So if the particle is trying to fall down a hill but not succeeding, that the friction is acting up the hill, and if the particle is trying to move up the hill, the friction acts down the hill. So it's like it just basically tries to stop motion. That's the job of friction. If you've got a smooth surface, then there's no friction. But that's a modelling assumption, because in reality there's no such thing as a smooth surface. The only other thing you might have is a push or a pull, and usually we use X, sometimes P, Q, those sorts of letters for a push or a pull. And don't forget that you're always drawing things coming out of the particle. So if I push, that's a hand, as you can clearly see. That's not my finest drawing of a hand, I'll admit. But anyway, say you push the particle, so the particle starts to accelerate in this direction. The force that you would draw would come out of the particle like that. So you're not drawing the actual finger, you're drawing the force acting on the particle, which would be going from the particle to the right. Now, don't forget acceleration. Acceleration is not a force, but we're drawing a force acceleration diagram, so we're going to add on, if there is any, the acceleration and the direction of the acceleration. And those are the things that are going to go on our force acceleration diagram. Really, there's only 3 types of force acceleration diagram that you need to worry about. A particle on the floor, a particle hanging from a string, and a particle on a slope. And if you can draw these 3, then you're fine. The angle of the slope is alpha. So let's think through our types of force. We've got weight. Well, they're all going to have weight going down, mass times gravity, going down towards the centre of the Earth, mass times gravity. Normal contact force, we've only got two of those. We've got the one on the floor, that will have a normal reaction force going perpendicular to the floor, and the one on the hill has got the normal reaction force going perpendicular to the hill. What about tension? Well, only one of these has got tension, and that's the one hanging from a string. So the tension is in the string like this. So we're not drawing the actual string, we're just drawing the forces, and the force tension in the string like that. Friction, well, friction depends on the situation. So I will assume that for the sake of drawing these, that this is a smooth surface first of all, so no friction, and this is not a smooth surface, so we'll have some friction. Now, I'm not sure which way the friction is going to act. You have to really think about it. At the moment, because the particle looks like no other forces are acting on it, it probably wants to go down the hill, in which case the friction is going to go up the hill. What else was there? Pushes and pulls. We might have something pushing our particle that's on the floor. So this is a push. Don't forget I draw it coming out of the particle like that. So that's a push. We might have somebody pushing this particle. I'll just draw their hand. Actually, I think I've got a little... yeah, there's a hand, but it's going the wrong way. So if they're pushing it that way, if somebody is using their finger to hold the particle like this onto the hill so it doesn't fall down, then we wouldn't draw it like that. We draw it like this. And actually, when you think about it, it's possible that that force, that X force, would actually, even though it's going not parallel to the hill, but into the hill horizontally, it might actually cause the particle to move up the hill if there was no friction. So you'd have to really think whether or not, if this was happening, whether or not your friction is going to act in that direction or possibly act in this direction. So you'd have to have a little think about it. I can't have both of them, I have to choose one. I can't rub out the other friction, I'll scribble it. Yeah, so just think about which way your friction is going. Okay, so that's all our forces. We've got weight, normal contact, tension, friction, any pushes or pulls that are occurring, and then don't forget acceleration. Now this one might be accelerating downwards. This one looks like it would be accelerating that way. This one on the slope, maybe it's not accelerating at all. Maybe the person's holding it on and the friction's acting, but between them they cancel out and there's no acceleration. So if there's no acceleration, don't worry about your acceleration arrow. If there is, think about the direction. We can create combinations of these three types of situations using some string. So for example, we could have something on the floor connected to something on the floor with a piece of string. Or we could have something on the floor or on a table, say, connected with string over a pulley to something dangling down. So there's all sorts of things. You can create basically any combination of these two things. You'd have something hanging with string, pulley, string, something else hanging, or you could have or something on a slope, string, pulley, and then the other side is a different steepness of slope, and then there's something there. So you can just have combinations, but essentially these are just two of the three that we've just looked at. And in terms of drawing the force acceleration diagram, what you do is you make it into two separate diagrams. So you just sort of get rid of what's happening in the middle and can treat it as two completely separate things and draw your force acceleration diagrams, exactly the same as before. So in the first situation, we've got weight, we've got reaction, got tension in the string, might have friction, not sure. In the second particle, we've got probably a different weight, M2G instead of M1G, different reaction, R2, R1, tension in the string, same tension or different tension? Let's come back to that. I'll put a little circle around it to remind us to come back to it. Same tension or different tension? And then maybe some thrust from an engine of a car or something like that. Oops, not T, that's the tension. There you go, thrust from an engine. So you just separate them out. So the pulley case, we've got tension, again, same or different tension? Come back to it. Second weight, first weight, like that. In this one that was hanging off a table in the left-hand side, we've got weight, we've got reaction, might have some friction, got tension in the string. Same tension? different tension, let's come back to that, and a different weight, then the two slopey things, you've got this weight, you've got reaction like that, you might have some friction opposing the motion, friction opposing the motion, thinking about which way it goes, tension in the string, same tension, let's come back to it. So you basically just draw two diagrams, so it's the same as the last situation, it's just there's two of them, and then we've got this issue of whether or not the tension in the string is going to be the same or not. Now don't forget, we're not drawing a force diagram, we're drawing a force acceleration diagram. So if anything is accelerating, then we need to put that on. So our hanging over a pulley thing, the heavier one will go down and the lighter one will go up. Will it be the same? I'm not sure, let's come back to that. Let's put the same for now and then think about it. If we've got something on a slope, maybe this one accelerates down that way and this one accelerates up that way. If we've got something on a table and then something else dangling down, maybe that one would accelerate that way and then that one would be pulling it down by falling off the table. Maybe we've got a car pulling a caravan or something, in which case they're both going to the right. Now notice that in the car and caravan situation, the accelerations are going in the same direction, but in all the other situations, the accelerations are going in different directions. Now that is a special thing about the car and the caravan situation, because the car and the caravan are accelerating in the same direction. We can actually, instead of separating this into two different diagrams and drawing them separately, we can actually combine them into one particle, the car-caravan particle. So this is the car-caravan particle, and the forces acting on the car-caravan are its weight, that's the combined weight of the car and the caravan, a normal reaction, any sort of driving forces, any resistive forces like friction and that kind of thing. And then this is the car-caravan system in one piece. Now the advantage of that is there's no tension. Tension in the tow bar becomes an internal force, so it's not there, so it's not in our calculations, and it makes everything a lot easier. So in the car-caravan situation, you've got two options. You can split it into two and treat them separately, or you can combine them together into a car-caravan system and draw it like that. You've got two options, and that's only because the accelerations are going in the same direction for each particle. All the other ones you'd need to split into two because the accelerations are going in different directions. Okay, so finally, why was I putting the accelerations as being the same for each particle and the tension in the string or the tow bar as being the same? Well, it's because we have a smooth pulley and light, doesn't really matter, but inextensible string. So it's the smooth pulley, which means there's no friction on the pulley, and that means that our tension will be the same. So if you've got a smooth pulley, then you can assume that the tension either side will be the same, the tension each particle will be the same. And because we've got an inextensible string, that means it doesn't stretch, it's not a piece of elastic. And because it's not stretching, basically it makes sense, right? If you're pulling something and the string won't stretch, then they will have the same acceleration. So these are modelling assumptions, that the string is inextensible and that the pulley is smooth, and you do need to know what those cause in terms of your diagram. So the smooth pulley gives you the same tensions and the inextensible string gives you the same acceleration, and the fact that the string is light means its mass is negligible. So for example, when we did the car-caravan system and we made it into a car-caravan system and we ignored the internal force of the tow bar, the mass that we would have here would be the first mass, the mass of the car and the mass of the caravan, but we wouldn't take into account the mass of the tow bar because we're considering it to be negligible. That's what that bit means. Okay, you should be able to draw your own force diagrams now. Force acceleration diagrams, don't forget acceleration.